classification model here. All right, and this is, I think, going to use the MNIST data set. Yes, all right. So let me again put the instructions over here. This data set is going to come back in a later project and be very important. Oh, I see a question. From the link posted yesterday, AdVox, which fools neural network. I read the original author's GitHub. Yes, absolutely. Very good. All right, and that's the last one today. We're going to do that thing I talked about yesterday. So let me get my AI model back here. Let's get rid of this old stuff, but move to trash and return. Okay, now we're going to get the next data set, which is a very famous one called MNIST. This is a bunch of numbers that were written down by American census takers and then digitized. So they're just written numbers. So we get a description of the data. All right. It's nice that it puts an arrow there. I haven't seen that before. It shows you which command is executing, and you can see down here as it goes. So it's fetching something from somewhere in this library, I guess like a GitHub repository or something. And then it's going to print a description. Here's the description telling you what this is, handwritten digits with 784 features and so on. And those are pixels. So now we're going to get a summary of it. We're going to print the shape of these. We're going to make X and Y be the data and the target. And we'll print a summary of what those are. So here's what the X shape looks like. It's just a bunch of arrays, 784 wide, and there's a bunch of them. There's 70,000 rows, and each row has 784 numbers. And here's the Y is the actual correct label. So the 784 values in this row define an image, and that is an image of a 5. And the next one is an image of a 0, and so on. So we can actually display the images, which is, of course, very useful. You can see what they look like with this code. That's going to print 100 of them in a 10 by 10 grid. And there they are. So just as you thought, these are just handwritten digits, digitized. And of course, this is kind of interesting. That one has errors around the edge, but they each have various defects, like this one is crooked and such. So we're going to try and learn with the machine learning how to identify them. So all we have to do is the same stuff we always do. We're going to split the data into training and testing sets, which this will do. And what we're going to do is take the first 60,000 of those 70,000 images and call that the training set, and the last 10,000 will be the testing set. Okay. Now, what we're first going to do is make a binary classifier. There are 10 categories from 0 through 9, but we're not going to solve that problem right away. We're going to start by solving a much simpler problem, which is whether it's a 5 or not. So we're going to make the Y be, if it's a 5, then it's true, otherwise it's false. So it's going to be to reduce this 10 category job into a 2 category job, which they call a binary classifier. So here's the training set, true 5,400 times, false 54,000 times, and the testing set is true 890 times and false 9,000 times, because only 1/10 of them are 5s and 9/10 of them are not 5s. So that's the training and testing set. Now we're going to make a linear model, which will look like this. Let me shrink it down a bit to fit it on the screen. And get this up here. All right, so the input image comes here. You break it up into 784 pixels. Then you feed them into this neuron, which will just combine all those signals with weights that can be adjusted. And this will just have one value output. And that value will be the probability, a signal that will be large if it's 5 and small if it's not 5, or the other way. That's called a binary classifier. All right, so here's the code that does that. As you see, really very little code here. It's just a couple lines that does it. This fits the model to the training data, and now I'm just going to print out the first few predictions for the first 3 images. So there it is, training. It's automatically choosing how many epochs of training. And remember, as before, there's this loss number on the right, which is the error, and it's going down. started at like 500, now it's down to like 200. It'll automatically decide when it's trained enough, which is so it's 160 rounds. I'm very amazed at how fast this is. 60,000 images, and each image is 784 pixels. This is handling a lot of parameters, but it just zips right by, and there it is. So for image 0, it predicted a 5, which is correct. For image 1, it predicted false because it's not a 5. So this is true because it's a 5. These two are false because they're not a 5. And so the first 3 predictions are correct. All right, and so now, to measure the accuracy of your model, one technique is cross-validation. In cross-validation, you split the training set into 3 portions, and you train it on 2/3 of the set and test it on the remaining 1/3, and then you do that 3 times. That's what this does, cross-validation. It will do a 3-way cross-validation to train it 3 times and test it 3 times. So this will take 3 times as long as what we just did before, approximately. Going to have to run through these epochs for 3 training all the way times. It was something like 150 epochs required to train one. Yep, it finished around 170 or something. Now it's going to do the second one up to 170 or so. And the point of this one is, the last one showed you how to manipulate input data in useful ways. This shows you how to test the quality of models in input ways, in interesting ways. So there it is, it's done. Took 10 seconds. And so here's the answer. The 3 times it did it, it was 95% correct, 96% correct, and 96% correct. So that's the result of how accurate it is. Now that sounds pretty good, but remember, 90% of the data is not 5. So if you just said false all the time, you'd be 90% correct. So 96% correct is not as good as it sounds. All right, so now, so this model is better than random, but it's not a very powerful model, and we'd like to get some more ways to measure its strength. So here's the confusion matrix. This is another way to express the quality of your model. And they'll perform a 3-fold cross-validation and return the predicted values. Right? I'm not sure I had to repeat the training, but anyway, that's what I did here. And now we're going to get the confusion matrix at the bottom of this. It's only 10 seconds. However, I think I could improve my instructions to not have to do this again. But anyway, I'll leave it as it is for now. All right, this is the confusion matrix. So this is the training set and the testing set. So it got 50, okay, let me get my instruction here. Okay, the first row contains most of the images. These are the non-5 images. And I shouldn't say training and testing set here. This is all from the training set. So you have, these are the non-5 images, and 53,000 of them were correctly identified as non-5s. These are the errors. 687 of them were incorrectly called 5s when they were not 5s. And the next row is the 5s. 3530 were correctly identified as 5s, while 1891 were incorrectly identified as something other than 5 when they were a 5. So these are the errors, and those are the true. And this is the false negative, where it failed to detect a 5, and this is the false positive, where it detected a 5 when there wasn't a 5 there. So now you can define a parameter called precision. Precision is true positives over all the positives, true positives plus false positives. So precision is the percentage of time that you correctly identified the 5. Then you can define recall. Recall measures the percentage of positive inputs that were correctly predicted. So this is true positives over true positive plus false negatives, another way to combine these numbers. And then you can define an F1 score, which is a way to combine these two numbers, the geometric mean of them, the product over the sum times 2. And this is a number that will be 1 if both the precision and recall are very high, but if either one of them is small, it will be small. So these are just various statistical ways to measure the quality of your model, and you can calculate them with simple code here. All right, precision, recall, and F1 score. So for this current model, the precision is 83%, the recall is 65%, and the F1 is 73%. A perfect model would be 1. All right, now we can play other games with this, and where it actually gets pretty important. There's a precision recall trade-off. Remember how this worked. We feed in the data, we get down one neuron. The one neuron has a signal. It's either low or high. Now you can choose where to put the threshold. By default, it'll put the threshold in the middle where precision is approximately equal to recall. And that is one way to make the model. But you could also choose to have a very high threshold, so it is very reluctant to say something is a 5, and then you will have the precision greater than recall. What you will have is almost no false positives. If you put the threshold up here, it will almost never call a non-5 a 5, but it will more often fail to detect the 5s. And if you put it down here, it'll be the opposite. You will almost never fail to detect a real 5. Anything with any signal at all will be called a 5, but you will now have more false positives where the non-5s are called 5s. And now you have to know what you're doing. If you were, for example, making an antivirus product, as you know, if you have an antivirus product, you really don't want false positives. You don't want it flagging innocent software as a virus and blocking it. That's very bad. So you would want to move the precision over here, where you're going to fail to detect some viruses in order to avoid false positives. There may be situations where you want the other one. You want to make very, very sure that you catch all of these things you're looking for, even at the cost of fingering innocent things with false positives. So you can view the raw output of the neuron here. It's called the decision function. This is the output of the single neuron in our model. It takes all those inputs. So here you see for the first 12 images what the value is, and you can see this is positive 2,000 for the 5, but negative numbers for the non-5s. Here's another 5, it's plus 4,000. So in general, having the threshold near 0 is the default, and that would have the effect we've seen there. And now we can try different threshold values here and see what effect that has. All right, I'm going to just try make a graph of different threshold values here. And looks like I repeated the training again, which I think was not really necessary. I could make this project run faster by cleaning up my instructions, but anyway, it's only 10 seconds. And I may try and clean these up later. At the time being, I'm racing to write new ones. So cleaning up non-fatal mistakes in the old ones is not a high priority. All right, now there should be a graph. There's the graph. So let me see if I can make it fit on the screen. All right, I'll shrink it a bit so it fits better. All right, so here's the threshold. If the threshold is near 0, you have equal precision and recall. If you make the threshold very high, you get high precision but low recall, which means it's very hard to be called a 5, and only things that are really 5 are called 5. And at the very top, you're only picking like a 3 or 4 or 5 5s out of the whole data set, which is why it gets really noisy. And down here, you've got the opposite, where you will even a very weak signal will be called a 5, so you always identify all the 5s correctly, high precision, but you have very bad recall, or very high recall. You always identify the 5s, but very bad precision. You identify a lot of things that were not 5s as 5s. So that's all I wanted to show you about that one. I think that's the end. Yeah, there's some flags to find here. All right, so let me stop recording this one.